Welcome back to Hansen Theory. So far, you have mastered molecular forces, Hansen space, Ra distance, red number, polymer behavior, solvent blend design, pigment-resin interactions, cross-linking and curing interactions, predictive troubleshooting, and multi-component formulation optimization. Now, we move into an essential real-world consideration: environmental and temperature effects on solubility and curing. Understanding these effects is critical because no formulation exists in a static environment. Temperature fluctuations, humidity, shear, and storage conditions all influence molecular interactions and coating performance. Let's start with temperature effects. Temperature influences three critical aspects: molecular mobility. Higher temperatures increase polymer chain mobility, solvent diffusion, and reactive group accessibility. Solvent evaporation. Volatile solvents leave the film faster at elevated temperatures, altering the effective Ra distance and red. Reaction kinetics. Crosslinking and curing reactions accelerate with temperature, but may become heterogeneous if diffusion limits exist. In Hansen space, temperature can shift the relative position of components. A polymer-solvent pair that is comfortably inside the solubility sphere at room temperature may move toward the edge or outside the sphere at high temperature due to faster solvent loss or polymer contraction. This is why coatings that perform well in the lab sometimes fail in production or in hot climates. Now, consider humidity effects. Water can act as a solvent, plasticizer, or disruptor of hydrogen bonding. In waterborne coatings, humidity influences red values dynamically. High humidity increases hydrogen bonding opportunities, effectively shifting polymers and solvents closer in Hansen space. A low humidity reduces molecular mobility, slowing curing and solvent penetration. Condensation on surfaces can lead to localized phase separation or defects. Next, let's examine shear and mechanical effects. Mixing, pumping, and spraying apply shear forces that alter polymer conformation and solvent distribution. Shear can temporarily reduce red by increasing polymer-solvent contact. However, if shear is excessive, it can destabilize pigment dispersions or break polymer chains. Minority-thinking engineers consider these mechanical factors when mapping formulations in Hansen space. Now, solvent evaporation during curing. Solvent loss is a dynamic event. As the solvent evaporates, polymer chains draw closer together. Ra distances between polymers, pigments, and curing agents change. A red may temporarily exceed 1 in critical areas, risking flocculation, phase separation, or incomplete curing. Predictive formulations anticipate these shifts. Multi-solvent systems are designed to maintain red 1 throughout evaporation. Co-solvents are selected to control drying rate and maintain polymer mobility. Additives stabilize pigments and reactive groups during solvent loss. Next, cross-linking kinetics under environmental variation. Curing reactions are highly temperature-dependent. At low temperatures, red values may remain high for reactive groups, leading to incomplete cross-linking. At elevated temperatures, reaction rates increase, but differential mobility of components can create heterogeneous networks. Minority-thinking engineers model these scenarios in Hansen space to select curing agents and solvent blends that maintain uniform red throughout the process. Let's address temperature-dependent pigment behavior. Pigments can interact differently at various temperatures due to surface energy changes. High temperatures may reduce pigment-resin Ra distance, improving dispersion, or cause thermal aggregation if red rises locally. Low temperatures may hinder dispersion or pigment wetting. Designing for a wide operational temperature range ensures performance consistency. Now, additive behavior under environmental stress. Dispersants, surfactants, stabilizers, and rheology modifiers can change their effectiveness with temperature and humidity. Some additives may crystallize or lose activity under extreme conditions, altering red and causing instability. Predictive engineers account for this by evaluating additive solvent-polymer pigment interactions under expected environmental conditions. Next, consider multi-component systems under environmental stress. Systems with multiple polymers, pigments, solvents, and additives have complex red dynamics. Temperature and humidity shifts can move some components out of the solubility sphere while keeping others inside. This can cause partial phase separation, haze, or uneven curing. Hansen theory allows engineers to predict which interactions are most vulnerable and adjust formulations proactively. Now, let's discuss industrial relevance. Production facilities may experience temperature gradients, seasonal variations, or variable humidity. Field applications, particularly outdoor coatings, face extreme environmental conditions. Minority-thinking engineers design formulations that are robust across these variations by maintaining RED 1 for all critical interactions. Next, predictive modeling of environmental effects. Engineers can simulate how RED changes during solvent evaporation at different temperatures, how humidity affects hydrogen bonding and polymer swelling, how shear during application affects pigment and polymer alignment. This allows proactive optimization rather than reactive troubleshooting, ensuring coatings perform reliably in diverse environments. Now, a common industry mistake. Many engineers test formulations only under laboratory conditions. They ignore environmental variability, assuming lab success guarantees real-world performance. This often leads to failures in production or end-use applications. Hansen theory guides you to anticipate environmental shifts and incorporate them into formulation design. Next, environmental effects on curing schedule. Curing times must be optimized for real-world conditions. Low temperatures may require extended curing or co-solvent use to maintain RED 1. High temperatures may require staged curing or evaporation control to prevent uneven crosslinking. Finally, minority-thinking engineers integrate environmental resilience into all formulation decisions. They design solvent blends, polymer selection, pigments, additives, and curing agents with temperature tolerance, humidity resilience, shear stability, and predictable RED values throughout the life cycle. This ensures coatings are not only chemically compatible, but robust under all expected environmental conditions, from production to end use. In the next episode, we will explore waterborne and high solids coating systems, applying Hansen theory to modern, eco-friendly formulations. If you want to engineer coatings that perform reliably in any environment, continue with this series. This is Hansen theory.